Hello, how are you? My name is Robert, and from now on I thank you for watching this video, in which I am going to review Ohm's law, and its application to the construction of voltage dividers, such as in high voltage probes like the Fluke 80K40, which allows measuring voltages of up to 40,000 volts, in low energy applications. But before continuing, I would like to ask you not to forget to drop a like if you find this video interesting. In that way, I will program new videos on this topic. And if you want to receive notifications of new videos, don't forget to subscribe to this channel and activate the notification bell. Ohm's law is probably the best known experimental physical law to electricians. This law receives its name in honor of the German physicist and mathematician George Simon Ohm, who enunciated it back in 1827. Ohm's law relates the voltage applied to a material, with the current that flows through it as a consequence of that applied voltage. Mr. Ohm, and many colleagues in his time, spent many hours experimenting with materials to discover this relationship between voltage and current. For this purpose they had instruments that were complicated to use, such as the torsion balance that we see in the image, used to measure voltages when a small magnetized needle that hung from a thread deviated. And since the best way to learn is by experimenting for yourself, now we are going to rediscover Ohm's law. But we are much more fortunate as we have an adjustable DC power supply, a Fluke 87V multimeter for measuring voltage and a Fluke 289 multimeter for measuring current, and as a material we are going to use a standard resistance that we can find in any electronics store. I am not saying its value, because the objective is also to discover it experimentally. The diagram is the one shown in the following image. We get down to work, and what we are going to do is build a table with voltage and current values varying the voltage of the DC source, from approximately 0 volts to approximately 30 volts. We measure the voltage and current at the ends of the resistance, and thus we obtain a series of points, which we can represent in a graph with the voltage on the vertical axis and the current on the horizontal axis, which will show us the type of relationship between voltage and current in this material, that is, in a standard resistance. As we can see, the graph obtained is a perfect straight line that passes through the origin. From our school days, we will remember that the mathematical equation of a line like this is: the function, y, is equal to the variable, x, multiplied by the constant k, which is equal to the slope of the line. In our case, y would be the voltage, and x the current, so we have V equals k multiplied by I. Which is precisely Ohm's law for direct voltage systems, which tells us that in materials such as metals, the current flowing through a conductor is proportional to the voltage at its ends, the proportionality relationship being precisely the resistance, R, of the material. That is, V equals R, multiplied by I. In our case, the slope of this line is approximately equal to 30 volts divided by 0.03 amps, that is, 1000 volts per amp. Therefore the ohmic value of the resistance we have used is 1000 volts per amp. As we have already pointed out, Mr. Ohm gave the name of resistance to this constant K, and to the unit that represents it, volts per amps, was given the name of Ohm, precisely in honor of Mr. Ohm. And if we measure the resistance we used, the value indicated by the multimeter is 1.058 kilo ohms, that is 1058 ohms, which coincides very well with the value obtained experimentally. As we have already commented, in the International Measurement System, voltage is measured in volts, current in amperes and resistance in ohms. Despite the practical importance of Ohm's law, this law is not considered as a fundamental law of nature, but rather an experimental law, as it is not fulfilled by all materials. For example, in semiconductors the resistance is not constant. Here we can see the typical graph that relates the voltage to the current in a diode, and as we see it is not a straight line as in a resistance. We can remember Ohm's law through the following triangle that relates these three parameters. In this way we can obtain these three relationships. The voltage is equal to the current multiplied by the resistance. The current is equal to the voltage divided by the resistance. And finally the resistance is equal to the voltage divided by the current. These would be the expressions of Ohm's law for DC circuits. For AC systems we must consider the impedance of the circuit and use vectors. Ohm's law is fundamental in electricity on a practical level. For example, in an electrical installation we must consider the section of the cables not only to be adequate depending on the current value in order to prevent wires from burning, but also taking into account the voltage drops that occur throughout the cables, since as we have seen, in a cable there is a voltage drop that is given by the product of the current and the resistance of the cable along its entire length. The designer of the installation must take into account the length of the cables, their section, resistivity, etc., to guarantee a maximum voltage drop that does not affect the loads. Perhaps in an indoor installation such as that of our houses, this aspect is not so critical, but if for example, we consider a long tunnel, an excessive voltage drop could affect the lighting of the furthest luminaires from the transformation center. Standards in each country establish maximum voltage drops. For example, the standard IEC 60364-5 DOS 52, in Annex G, states that the voltage drop between the origin of an installation and the load connection points should not be greater than the values indicated in the following table, expressed with respect to the nominal voltage of the installation. In this way, if we consider a low voltage line, with a nominal voltage of 230 volts, and a maximum voltage drop of 3%, the difference in voltage between the two ends of the line should not be greater than 6.9 volts. Now let's go back to our circuit and make a modification to it. Let's connect in series with the resistor that we had, another resistor of equal ohmic value, and apply voltage between the ends of both resistors. Now the Fluke 289 multimeter measures the total voltage applied to the two resistors, R1 and R2 in series, and the Fluke 87 multimeter measures the voltage at the ends of the R2 resistor. What will be the voltage across R2? If the two resistors are exactly the same, Ohm's law tells us that the voltage across R2 will be half the total applied voltage, but we are going to verify this by making the measurement. As we can see, the total voltage is 29.48 volts, and if we divide by 2, it gives us a value of 14.74 that coincides very well with the 14.73 volts measured in R2. In this way we have built a voltage divider that reduces the voltage by half. By varying the relationship between R1 and R2 we can vary the output voltage. For example, if we want to reduce the voltage a bit more, we will have to make the value of the resistance R1 greater than the value of R2. Suppose for example, that R1 is equal to 10 kilo ohms and R2 is equal to 1 kilo ohm, then Ohm's law tells us that the voltage at the ends of R2 should be 1/11th part of the total voltage V. Let's do the measurement again to check it. The total measured voltage is 29.58 volts, and if we divide this voltage by 11, it gives us a value of 2.68 volts, which coincides very well with the measured value of 2.70 volts, with an error of less than 0.5%. In this way we can properly choose the two resistors to build a voltage divider according to the voltage reduction we want to obtain. This is the technical basis of the Fluke 80K40 high voltage probe, and thanks to it, together with a standard multimeter we can measure AC and DC voltages of up to 40,000 volts. This probe is valid for Category 1 systems, which implies using it in circuits with limited energy, such as in high voltage circuits used by cathode tube televisions with flayback type transformers, or in photocopiers, laser printers, etc. They are generally not capable of delivering very large currents. For example, in the case of flayback transformers in older televisions, they could be a couple of milliamps. In these applications, a direct discharge, despite being unpleasant, should not normally pose a risk to the technician's health. As we see in the chart of time versus current risk zones according to the standard IEC 479-1, for a couple of milliamps we would be in a safe zone for most people. On the contrary, this type of probe is not designed to be used in medium voltage electrical distribution systems, in which an electrical discharge would have fatal consequences for the technician as there is no current limitation to protect it. If for example we consider an average value of the resistance of the human body of 1000 ohms, then a voltage of 40,000 volts would suppose a current of 40 amps, and that would definitely place us in the high risk area. As we can see in the diagram of the Fluke 80K40 probe, it is composed of two resistors, one of 999 megaohms and the other of 1.11 megaohms, which form, as in the previous examples, a voltage divider. As we want to use it in low power circuits, we must avoid taking a lot of current from the circuit, that is, the probe should have a high input impedance. If you want to learn more about what the input impedance of a multimeter is, you can check this other video. To increase the input impedance of the probe, it uses mega-ohm resistors. Because of this, the input impedance of the multimeter itself must also be taken into account when measuring the voltage. For this reason, to use this probe it is recommended to use multimeters with an impedance of 10 mega-ohms, like many of the Fluke multimeters. In this way we can directly use the value shown on the display by simply multiplying it by 1000. As we can see, the resistance R2 would be in parallel with the input impedance of the multimeter, so that the equivalent resistance that we obtain between R2 and the 10 mega-ohms of the input impedance of the multimeter gives us a value of 1 mega-ohm. In this way, the total impedance of the probe will be 1000 mega-ohms, and when applied to a 40,000 volt circuit, it will take a current of 40 microamps, which will lead to a voltage drop of 40 volts at the input of the multimeter. In this way we confirm the indicated transformation ratio of 40,000 input volts and 40 output volts. In case the multimeter has a different input impedance, then the indicated ratio of 40,000 to 40 will not be correct, and an additional correction factor must be applied. If, for example, the multimeter has an input impedance of 1 mega-ohm, the value shown on the display should be multiplied by 1901, instead of by 1000, to obtain the correct high voltage value. The use of this type of probe is very simple. We see that it has a long tip that we must apply to the high voltage circuit and a crocodile connector for the high voltage reference, and on the other hand, it has a double banana connector that we connect to the voltage input of the multimeter. We select AC or DC in the multimeter depending on the voltage we want to measure, and if the multimeter is in auto range mode, it will directly show the value on the display. If it is not auto range, we will have to select the appropriate range, dividing the range of the high voltage to be measured by the attenuation ratio of the probe. And so we have reached the end of this presentation. In this way we have remembered Ohm's law, that provides us with a fundamental equation that relates voltage, current and resistance in ohmic materials such as metals, through the well-known formula voltage is equal to current multiplied by resistance. We have also seen the application of Ohm's law to build voltage dividers, and especially we have seen its use in the Fluke 80K40 high voltage probe. I hope this video has been of interest to you. And as I mentioned at the beginning, if this video has been interesting for you, don't forget to drop a like, so that I can know that you liked it, and I can program new videos on this topic. In future videos we will see more technical concepts on electrical measurements, so if you don't want to miss them, don't forget to subscribe to this channel and activate the notification bell. Thank you very much for watching this video. See you soon.